morning. We are now doing lecture 14 in the second module. The topic is still review of basic structural analysis. We will be looking more closely at the slope deflection method and the moment distribution method, which we introduced in the last class. This is described in part 5 in the book on structural analysis. But before we continue, I'd like you to see this big picture on this board. Here I have shown a typical continuous beam. In this particular example, you have 3 spans. All the beam segments are prismatic. They have constant EI. Our idea is to be able to draw the bending moment diagram and the shear force diagram. To draw these diagrams, we need to know the end moments, right? If we know the end moments, then each beam can be treated as simply supported with known end moments. We can analyze each segment separately, get the reactions, and for each element you can draw the shear force and bending moment diagram. So let us be very clear, our real objective is to be able to draw the bending moment diagram and the shear force diagram. Now in the displacement method of analysis, we try to get to know these moments by relating them to displacements. That is why it is called a displacement method. Now what are the unknown displacements? We need to worry only about displacements at the joints. There are 4 joints in this example, A, B, C and D. None of those supports translate in this example. So there are no chord rotations, I am making it simple. So we have 4 rotations at the 4 joints, theta A, theta B, theta C and theta D. In this example, end A is fixed, so theta A is 0. You may get a problem as we did yesterday where theta A is not 0, but it is known, you have a known rotational slip, it does not matter. Now in terms of theta A, theta B, theta C and theta D, you can write expressions called slope deflection equations for all the end moments. Each beam segment has 2 end moments, one at the left end, one at the right end. We assume them to be clockwise positive. So the equations look like this, right? I have written them out and they are very easy to write down. MAB is MFAB plus 4EI by L into theta A plus 2EI by L into theta B, and in this example there is no chord rotation, so you can leave out the minus 6EI by L into phi AB. Similarly you can write for MBA, right? Now you will notice that MAB and MBA, the end moments in this segment, do not depend on rotations that happen far away. What happens at theta C is not reflected in these equations, right? That is the beauty of it. Each segment, the expressions for the end moments depend only on the end rotations of that segment. So you will find when you write it in a matrix form, you will find that these values are 0. MAB is MFAB plus 4EI by L1 into theta A plus 2EI by L1 into theta B plus 0 into theta C plus 0 into theta D. Similarly you can write for the other 2 segments, for the segment BC and for the segment CD. For the segment BC you have dependence only on theta B and theta C, the second and third columns. For the segment CD you have dependence only on the third and fourth columns, which reflects C and theta C and theta. It is very simple, it is not difficult. Now with the help of these slope deflection equations, you can find the end moments and thereby draw the bending moment diagram and shear force diagram, provided you know these unknown displacements, unknown rotations. How do you find the unknown rotations in displacement methods? By invoking equations of equilibrium. Now, corresponding to each unknown rotation, in this case, you have an equilibrium equation. Now, since theta A is 0, it is known. So, really speaking, you need not include it in this unknown displacement vector, you can just knock it off because theta A is known, which means the first column we need not have written at all, though it is there. If theta is not 0, you need to bring it into being, but if theta is 0, you do not need to write this first column, or you can write it and delete it. Now, you have 3 unknowns, you need 3 equations, and those equations are equations of equilibrium. So, obviously they must use these slope deflection equations. Now, if you can relate these 2 equations to this concentrated moment acting here. If this concentrated moment were not to act here, then these 2 moments should be equal and opposite. Why? Why? You can say to satisfy equilibrium, but you can also use Newton's third law and say every action has an equal and opposite reaction. When you join them together, there should be nothing left over, they should cancel each other unless you have a concentrated moment as you have in this case. So, the equation of equilibrium written algebraically correctly, because all moments are assumed to be clockwise positive, is MBA plus MBC is equal to whatever moment is acting there, in this case M1. At the second joint C, MCB plus MCD is equal to 0 because there is no concentrated moment acting there, and at this last support MDC is equal to, in this case, the concentrated moment M2, right. So, you have 3 equations, you substitute these expressions in those equations, you have got 3 simultaneous equations, you can solve for them, find the unknown rotations, plug them back into these equations, get your end moments. After you have got your end moments, you draw these free bodies, draw your reactions and draw your shear force diagram and bending moment diagram. Is it clear? It is beautiful, it is simple, it is clean. In this method you do not have to worry about fixing the unknown rotations and all that, you can do it mechanically. In fact, this is how all the books teach you, but we are trying to take some more advantages. What is the additional advantage we take? We reduce the degree of kinematic indeterminacy to how much? We reduced from 3 to 2. How do we do that? How do we do that? We realize that it is a waste of time to bring this equation because you know the end answer. This is not an unknown. So, we do not waste our time trying to calculate theta d even though it is unknown, because MDC is known. I do not need to write this in terms of an unknown theta c and theta d, I do not waste my time. So, I take advantage of that and I say I do not need to know this. So, right in the beginning I make that statement, I do not need to know this, which means I leave it as it is, I do not arrest it even in this picture. Even while drawing my fixed end moments, I let theta d operate, which means I am dealing with a propped cantilever when I draw these fixed end moments, in which case I write here this is equal to M2 and I do not even include it here, and here I do not do this calculation, but instead I do this calculation, that is I find out the fixed end moment for a propped cantilever, which I distinguish in notations by adding a naught out there, MF naught CD. Is it clear? So, I do not need to write this equation, it is not required. and I eliminate this column, it is not there. So I just have two columns. I just have theta b and theta c, but there is a correction I need to do. I have to, since I removed this, I have to replace this as 3, that is all. Don't you think this saves you tremendous time? You will find that solving 2 simultaneous equations is much easier than solving 3, and you know the amount of work involved as the order goes up is extremely non-linear. Have you got the hang of this? I hope this clarifies some of the doubts you had yesterday. Good. Now let us go ahead. Let us look at this problem where you have a support settlement at B. What is the degree of indeterminacy here?
2.
It is 2 in the old fashioned conventional sense, because theta b is unknown and theta c is unknown, but if you do it the smart way, it is 1. Oh, we are talking of, by the way, kinematic indeterminacy. Perhaps when you say 2 you refer to static indeterminacy. You forget all about static indeterminacy while you are doing displacement methods, only think of kinematic indeterminacy. Is it clear? Theta b. So how do we do this problem? Well, we have another method called moment distribution method. See, the big difference between moment distribution and slope deflection is, in slope deflection you explicitly find theta b and theta c and you substitute in these equations, but you are really not interested in theta b and theta c. Moment distribution method recognizes that and it says, don't waste your time calculating all this, get these moments directly by doing a distribution of whatever moment you get at the artificial fixity point. So that is a clever iterative method. Both options are there. This will give you an exact solution, the other may or may not. Okay, so in this problem you do not have any fixed end moments due to external loads, but in moment distribution method, unless you have some fixed end moments, you cannot do the balancing and so on. So what we do is we arrest that theta b, we say theta b is 0. Incidentally, you get chord rotations known, that is if the deflection is 6 mm, it is 0.006 by 4 for AB and it is minus 0.006 by 2 for BC. Why is it minus? Because you join ABC with a straight line, in this case AB dash C, and if the chord rotates clockwise, you give it a positive sign, if it rotates anti-clockwise, negative sign. So clearly BC is having a negative sign. So you have these additional fixed end moments, that is the language we use in moment distribution method, where for AB, when you arrest B, both ends are fixed, so you know the end moments you develop is minus 6 EI by L into phi, remember last class? But for BC, it will be minus 3 EI by L into phi because you are dealing with a propped cantilever when you are fixing B. Is it clear? Remember last class? So are you comfortable with these two equations? You get them from this is a known sway problem, the chord rotations are known. The difficulty comes when you have unknown chord rotations, which we will see later. So once you have these moments, what should you do? You can distribute them, you can add them up. Well, you have MFAB as minus 180, MFBA also is minus 180, all coming from chord rotations. In case you had some intermediate loads, you have to add those effects also, and MF not BC is plus 360. Why is it plus? Because it is minus of minus, you understand, it is minus 3 I by L into phi, but phi itself is minus because it is anti-clockwise. So you have to get this correctly, then you can do the distribution table. Remember we did this problem last class, so we had already calculated the distribution factors. So you write them neatly in that third row, fixed end moments are minus 180, plus 360 and of course 0 at the propped end. What do you do now? Okay, how did you get these fixed end moments? By arresting theta b, but you had no business arresting theta b, so you let go of it, you release that moment. So you should have a net moment there equal to 0. So the net moment there right now is minus 180 plus 360, which is plus 180, which you have to balance that's why it's called balancing. How do you do that? Yeah, you distribute it in proportion to the relative stiffnesses, just multiply it by 2 by 5, 3 by 5, you get those numbers. When you do it manually, you first put the minus sign to remind you that both will have a negative sign, then you fill in those numbers. But in this operation you should also do a carryover, but you carry over only to the left end A, not to the right end B, because left end A only is fixed. The carryover factor is plus half, so half of minus 72 is minus 36, and that's it. You've done the balancing. This is called a one cycle distribution. You've got the exact results, and many problems can be done very fast in this method. You add up the total, you got those moments. Then you can draw the free bodies, you can draw the bending moment diagram. Is it clear? So I have demonstrated in these last few problems how to solve problems with known support movements, either they are support settlements or they are rotations. You can, now let us do another problem with loading. Okay, this looks difficult, but actually there is a symmetry which you should take advantage about. There is a beautiful symmetry both for the structure and for the loading, and therefore for the response with respect to C. So you can cut that structure into half. You can either take the left half or you can take the right half. So you have reduced the difficulty in the problem. What is the degree of indeterminacy?
2 actually, but
2 actually, theta B and delta C, but you can, yeah, you can avoid delta C because you can modify your relationships. So theta B only is the unknown, right. So in the first few problems we do simple problems where you can reduce everything to one unknown. So single unknown rotation theta B, degree of kinematic indeterminacy is 1. What should you do now if you are doing moment distribution method? You should find the fixed end moments. How do you do that? You arrest only theta B, do not arrest delta C. If you arrest delta C, then your indeterminacy is 2, but we are not doing that, we are making it simple. So how do you do this? You arrest it, your fixed end moment, I think by now you know the formulas, you can get those values. MFAB and MFCB are easy to calculate. Sorry, you have both MFAB, MFBA and MFBC and MFCB. Is it clear? We have discussed this earlier. I think you know how to do it. Okay, we have done this earlier. Please be careful though, when you are finding for M for this span, it is best to visualize this with a double span with a load also acting on the right half and work out the fixed end moments for that. That is how you get MFBC, right. So you have to take the effect of not only this load and the double span, but also the other load which occurs here with the correct values of A and B. You need to do this correctly. I think we discussed this earlier. But as far as the middle moment is concerned, which is the sagging moment, you can take a free body and do it. It works out to this. Okay. So you know how to calculate fixed end moments. Then what do? What's the next step you need to know? You need to first, before the distribution table, you need to write down the distribution factors. How are you going to distribute the moment at B? So you have to do this and the carryover factors. So you do it in terms of relative stiffnesses. KBA is to KBC is 4 EI by L is by EI by L. Is it right? Because you are dealing with a cantilever behavior for span BC. Remember those 3 magic numbers. It is either 4 EI by L or 3 EI by L or EI by L. In this case it is EI by L for the right span. And can you work out those ratios? It comes to 2 by 3 is to 1 by 3, right. What about carryover factors? Tell me. If you distribute at B, you have to carry over to A. How much do you carry over? Plus half. You also have to carry over to C. How much would you carry over? Plus or minus? No, it is minus. It is a cantilever. Cantilever will always have equal and opposite moments. So that is the only thing you need to remember. Actually you have only 3 numbers possible. Either it is 0 when you have a simple support, or it is plus half when you have a fixed support, or it is -1 if you have a guided fixed support. Is it clear? Only 3 carryover factors possible. When it is 0 you do not mention it, so it is either +½ or -1. Then you draw the table. The table will look like this. Are you now comfortable with this? Write down the distribution factors, write down the carryover factors +½ and -1, write down the fixed end moment in the first column. Those are those numbers which you calculated, -20, +20, -35, -5 in this problem, and then what do? Where do you distribute? Only at B, only where you have the unknown rotation. So that is easy to do. Actually in your calculators you have, if you press the into twice, you can do any number of distributions. You have to work out ways of using your calculator and do this fast. Okay. So you distribute it, make sure when you add it up everything turns out to be 0, and you do a carryover. So that +10 carries over to AB as +5, and to CB the +5 carries over as -5. That is it, and put that arrow to help you understand, and add it all up. It is all over, it is balanced. One shot. I mean, this problem if you were to do by the force method would take you a long time. It is very powerful. You have reduced the complexity of the problem. And then once you have done this, draw your free body diagram and bending moment diagram. You can do the same problem by slope deflection method, by this method. How do you do that? Well, first you take advantage of symmetry, find out the fixed end moments as we did in the last. So this step is common, but do not find distribution factors, instead write down the slope deflection equations. How will they look like? Well, for AB and BA it is straightforward. It is the same as these equations except that you also have -6EI by L into phi wherever it is relevant. Is it clear? For AB it is clear. How will you write it for BC? You have to use those modified expressions. So it is MFBC plus EI by L into theta and minus EI by L in the second equation because of the cantilever action. Okay. That minus is taking care of that carryover effect of -1. Do you have doubts with this? You can go back to the earlier class and see we worked out the modified slope deflection. Once you have written this, what should you do? What is your next step? Equilibrium. What is the equilibrium equation? At B, MBA plus MBC equals 0. So pull out the second equation and third equation and add it up to 0. You can solve for EI theta B straight away. And after you found this, what will you do? Put them back, put that value back into those equations and get the answer, right? Easy. So you have a choice and I leave it to you. You can do either the slope deflection method or the moment distribution method or the proper displacement method where you use a physical approach. You can still solve this problem. It is not difficult. Draw the free bodies, draw the shear force diagram and draw the complete bending moment diagram. Okay. I am going fast because these steps are easy for you to understand. Shall we move ahead? Okay. Let us take a little more difficult problem, apparently difficult but really not. We have done this problem by force method. Okay. Now what is the degree of indeterminacy in this problem? Kinematic indeterminacy. Actually 3 because theta B can deflect, actually more than 3 if you assume axial deformations also. So theta B can go up or down, move left or right, so 2 translations. Every joint has 2 translations and 1 rotation except the fixed ends at A and E. So you have 2 joints which can move like that, B and C. So actually it is 6. If you ignore axial deformations it reduces to 3, theta B, theta D and the sway of BD, right, but there is symmetry here. So that sway is 0. So you have only theta B and theta D, but even that you can reduce. Both are equal and opposite. So you can do all that, but it is much easier to just cut the beam at C. Okay. So this is the deflected shape, take advantage of this, just do this. Okay, now it can't move, only theta B can move. So you should do this, it is the easiest thing you can do, single unknown. How long will it take you to solve this? By the way, before we solve this, tell me the moment at A, is it related to the moment at B in the column AB? Yeah, it will be just half. So even that you know in advance. Okay, it will be half because there is no lateral load on AB, so it is a carryover. So a single unknown. Now slope deflection method, find the fixed end moments. AB has no fixed end moments, BC has fixed end moments. How will you calculate them? By the way, when you cut that beam at C, that 200 kilonewton constant load in the middle will also get cut equally. One half will go to the left span and the other half will go to the right. Okay. So this is easy to, can you tell me the formula for MFBC? Minus
MFBC.
MFBC or BD or whatever you want to call it. Isn't it due to UDL? You should take the full span now. Minus 50 into the full span 6 squared divided by 12 minus 200 into 6 by 8. These are standard formulas, right? Can you tell me what is MFCB? You please do it yourself, tell me. You have to write that also. MFBC is clean, MFCB is what you get in the middle. Due to a UDL, what will it be? WL squared by?
L square by
WL squared by 8 is what you get when you have a simply supported
WL square
span.
by 12.
When you have a fixed beam, fixed, the end moments are WL squared by 24 and the middle moment is WL squared by, this is 12, the middle will be 1 by 8 minus 1 by 12, which is 1 by 24. Now it is best that you do not worry too much about formulas and you go straight to the free body, you will never make a mistake. For example, in this problem, what we are trying to do is, we are trying to find out what happens due to this loading, right. This is 100 kilonewton, this is 50 kilonewton per meter and the span is 3 meters, right. This is B and this is C. Now we have already found this out, okay. It is a hogging moment and the value is 300 kilonewton meter, right. You also know that there is going to be no reaction here because it is free to slide down. So the entire reaction goes here. How much is that? How much is that? 100 plus 150 is 250 kilonewton. There is no reaction. The only, sorry?
We have only UDL plus also concentrated load is there.
Yeah, I have shown you that calculation on the screen. Okay, after calculating this, it is easy to calculate this. How much will this be? Just take the free body and do it because there is no load here. So this will be 250 into 3 minus 50 into 3 is 150. So of 50 into 3 squared by 2, do you agree? And this will have no contribution, no lever arm, minus 300. How much does this work out to be? This is the easiest way to calculate that moment. How much is it? It will turn out to be 225, but please note it is anti-clockwise. So if you want to write it as MFCB, you should write minus 225. So here my suggestion is don't use formulas, use your brains, okay, just draw the free body, clear. After you have got this, write down your slope deflection equations. MAB is MFAB plus 2EI by L into theta B and MBA is MFBA plus 4 EI by into theta B. Theta B is your unknown. You can club it along with EI. MBC is MFBC plus EI by L. Now here the beam has a second moment of area which is 2I. So you should put that, don't lose that, EI by L into theta B plus and minus. Is it clear? So with some practice you can master this. Write it nicely in a matrix form. What is the next step? Up to this stage if you do correctly you will not go wrong. What is the next step? Equilibrium. What is equilibrium?
M at B is
M at B is 0, which is MBA plus MBC is 0, right, because there is no net moment acting there. Substitute, solve the equation, you get EI theta B, then plug it nicely into those equations, you got the answer, then draw the free body diagrams. All this you know, draw the we have done the same problem, shear force diagram and bending moment diagram. What is very interesting is that moment at A is exactly half that you get at B in the column. Is it clear? Very easy. So you see, compared to the force method, this was much easier, much faster. Okay, and you can draw the deflected shape and mark the points of counterflexion, see how nicely they match with the bending moment diagram. You know which side is tension, you have a clear understanding of this kind of behavior. Okay. If you want to do this by moment distribution method, you are welcome. Similar exercise, find the fixed end moments which we have already done. Now do this calculation. How do you get the distribution factors? Tell me the factors at B. dBA is to, give me the answers. I am not going to give you the answers, give me the answer. It will be KBAs to KBCs, 4 EI by 4 is to E into 2I by 3, straightforward, okay, which is 3 is to 5 is to 2 is to 5, not difficult. What about carryover factors? To A it is half, to C it is minus 1. Right, plus half and minus 1, clear? Now
at B we do not have any roller support kind of thing. It may
whether
things like,
let me ask you, when you had the continuous beam you had no problem. This is a in the continuous beam you had a reaction at B, you had a vertical, here also you have that, it is AB which is taking it. So AB is referred to as a beam column. So for you as beginners you find it a little difficult to relate the continuous beam to the portal frame. Yeah.
Sir, does here B deflect or not?
It does not deflect. B does not deflect because AB is inextensible, axial deformations are negligible. Here also B does not deflect, okay, here AB was horizontal, there AB is vertical, do you have a problem with that? So it is the same philosophy, is it clear? But you kind of turned it around 90 degrees, so you had a little doubt. But what is common to the portal frame, and this is in both the joint is rigid at B. Here the included angle between BA and BC was 180 degrees, there it is 90 degrees, that is all. But theta B is same for both BA and BC, clear? Good question. Next, draw the distribution table. Now the fixed end moments are only in BC and CB, minus 300 and minus 225. Distribute 300, what will you get? 180 and 120. Do the carryover, add it all up. How simple, how elegant, this is called one cycle distribution, and you get the answers. So if you look carefully, if you got the first type of problem, single unknown with a single joint moment, you are very lucky, it is very easy to do. If you have intermediate loads but still single unknown rotation, it is not too bad, it is just one cycle distribution. If you have multiple unknown rotations, you have to do simultaneously distribution at many joints, it is a little tricky, we will look at that shortly. But if you have sway, if you have support settlements which are not known in advance, then it becomes more complicated. But the important thing is, always when you do things manually, do minimum work, take advantage of reduced indeterminacy. So in some cases involving sway, it is possible to ignore the translational degrees of freedom by using modified element stiffnesses and modified fixed end moments. Let me demonstrate that. Take this problem. In this problem, which is basically a half of a portal frame ABC, you have a concentrated moment acting at B. What is the degree of kinematic indeterminacy actually, assuming actual deformations to be negligible? What are the two? Theta B and delta BC. Okay, what is the deflected shape going to be? Will it sway to the right or left? Obviously right. Supposing you did not have the beam, you had just a vertical cantilever, it will go to the right. So that is a deflected shape. Okay. Now we are trying to take advantage of the fact that cantilever behavior we know. So why do we not take advantage of that and say, and we know the modified stiffness for BC, so we say we do not arrest delta BC in our primary structure. If you do that, you get a tremendous benefit. So your only unknown now is theta B. Let us see how to do this problem. Your fixed end moments are not there. Okay, MFAB, MFBA, MF0 BC is 0 because there is no intermediate loading. That concentrated moment is being shared. It's going to the node. It's not going to any beam element, so it will be shared by both the elements. Your slope deflection equations for the vertical element, MAB is MFAB minus, see it is a cantilever behavior, you are allowing the top to move. If the top did not move, then it is 4 EI by L. Now the top is moving and you are arresting theta B, so you get MFAB, and do not you agree, you get minus EI by L into theta for MAB and plus EI by L into theta for MBA. The carryover side will always be minus. Are you comfortable with this or not? Do you want me to explain this? Good. So be bold and ask. See this, what we are saying, let us take this element AB. This is fixed here, right? This it is a funny thing, it can move, but there is a rotational spring here. This is a real problem, the real modulus is this can move to the right. Now if I want to find an expression for MBA, AB, what I do is, so this has a theta B, I first arrest the theta B. So when I arrest the theta B, I am saying it is this and this, because I am not arresting the translation, I am arresting only the rotation. So let us say there was a load acting here, then I should, this will give me my MF, from this I can get MFAB and MFBA, right, supposing there was a load, in this case there is no load. Then I should release this fixity, take that beam, now I am just applying, I am letting it translate, I am applying so that or if you wish to look at it this way, I am now letting it rotate by theta B, but allowing it to translate. So the deflected shape will be Are you getting it? And this is theta b. Now if something like this happens, what do you think the moment will be? It is clockwise, it will be EI by L into theta b, and what do you get here? Equal and opposite, EI by L. So a little thinking and you can get it. That is what those equations mean. Is it clear? It's a little more tricky than the previous case, but it saves you a lot of effort. If you really are not wanting to take advantage, treat it as a problem with sway, which we have not covered till now. You can do it later, but if you take advantage, this is what it looks. Is it clear? Did this help? Okay. Equilibrium equation, solve it, plug it back, write the equations, you get the answers. Okay, you get that moment of 50 kilonewton meter is shared by the beam and the column. The beam takes 44.44 kilonewton meter and the column takes 5.56 kilonewton meter. Clear? Okay, let us say you want to do it by moment distribution method. It is even easier. What will you do? Same fixed and moment calculations. Okay, here in moment distribution method, mind you, you are in trouble if you do not have fixed and moments to balance. So you have to create fixed and moments. So this is a clever method that I am showing you here. You imagine that 50 kilonewton meter was transmitted to the joint B by means of some rigid link. I have shown a cantilever there. That yellow bit sticking out is an imaginary rigid link. If you put a moment at the end there, that will reach the joint B, right? But now I have got a member with a fixed end moment. So it is a clever trick that I am doing, which is very useful to do. So I have an element dB and I have a fixed end moment in that MF BD equal to minus 50. Do you get it? But that is a cantilever. Okay, I am doing it just to enable me to do the moment distribution. This is how you handle concentrated moments in moment distribution method. You do not need to do this for slope deflection method. Work out the distribution factors. For the vertical element, which is the cantilever, it is EI by L. For the horizontal element with the far end hinge, it is 3 EI by L, isn't it? 3 EI by L. So if you work out the distribution factors, it works out to 1 by 9 is to 8 by 9, and your carryover factor will be minus 1 to the end A. Draw your table, do a single distribution. That element BD is only a device, so I put it in parenthesis. You do not have to worry about it from the design point of view. Do a single distribution, 8 by 9 of that 50 kilonewton meter goes to BC and 1 by 9 goes to BA and gets carried over to end AB. That is it, straight away. So it is a beautiful, powerful method of solving these problems. We will now, yeah, yes. We are allowing horizontal movement for the element BC. For the element BC, let us say I have a simply supported beam with rollers, let us say both are roller supports, and I apply loads on it. Will the behavior change if it moves horizontally? That is what is happening here. That 3 I by L is the relationship of the moment at B in that simply supported, in that BC. So let it sway like a rigid body, it does not make a difference. Do you get it? In fact, this question should have come in the slope deflection method also. There also we did 3 EI by L. Is it clear? Does it clarify? No, EI by L for AB. See, both these are same. You see this and you see this. I forgot to explain this. This is 3 EI by L. Both methods are identical. You do not put, the horizontal beam BC does not behave like a cantilever, it behaves like a propped cantilever when you arrest theta B. Do you understand? So you have to use the right, I told you it is 1, 3 or 4. either EI by L, 3 EI by L or 4 EI, use the right one at the right place, okay. So we will now look at multiple unknown rotations. Take this problem, similar to the problem I have shown you here, so I can go faster since I have explained this. What is your degree of indeterminacy? Which are the 3? Actually it is 5, theta A, theta B, theta C, theta D, theta E and delta E, it is 6. Oh my God, 6. This problem has been solved in other books where they have reduced it to 4, and that is a good thing to do, because you see that overhang part is statically determinate, you can throw it off. Theta A, theta B, it is actually 5, right? Yeah, theta A, so it is 6, it is 6, right. Now what many people do, and this is a clever thing to do, is throw away that cantilever, throw away that overhang, that is anyway statically determinate, and replace it with a constant moment 60, which is like in this problem. So you got rid of 2 indeterminacy there. So you still have at D. So what is the indeterminacy here? It is 4, okay. It can be 2. A is a simple support, D is a simple support, you know the moment at A is 0, you know the moment at D is 60. Is it clear? So that is a clever thing to do. So we make it 2. So from 6 we went to 4, we went to 2, just theta B and theta C, okay. How do we do this? First you arrest those 2 and find the fixed end moments. What are those fixed end moments? They are very easy to calculate. You can draw them longhand, right. You need to find MF naught BA first. What is that value, tell me, due to a propped cantilever? What is MF naught BA? Okay, let us say it is a fixed beam. What is it if you have a load in the middle? WL by 8, plus or minus? Right side will be plus, right. If it is propped cantilever, it will get enhanced by a factor 1.5 times, isn't it? In a propped cantilever it gets enhanced 1.5 times. So that is it. So you get, so the first answer you got, MF naught BA you got, okay. Why is it 1.5 times? You go back to the earlier discussions, you will see. Can you find MFBC and MFCB? That is easy, okay. You can use those formulas and get it, WAB squared by L squared and WA squared B by L squared, right. How will you get MF naught CD? So shortcuts you should take only if you know how to get these answers. Due to that 220 kilonewton, how much will it be? Here it is capital W, 220 is the total load, WL by 12 if both were fixed, but you have to multiply by 1 and 3 by 2, so it is minus that. Then that 60 kilonewton meter also has an effect in that fixed end moment. How much will get spilled over to the fixed end when you apply 60 kilonewton meter there? Half, that is your carryover factor. So it is brilliant if you understand every step that you do, it is half. Does it make sense? So you write WL by 12 into 1.5 plus that moment that you get at the free end D, half of it in the same direction, so plus half. You got it? Any questions on this? Everything depends on, your shortcuts depend on your ability to think through everything. Is it clear? Once you have done this, write down the slope deflection equations, they are straightforward. You will use 3 EI by L for AB, 3 EI by L for CD, but not for the middle span. Write them down in terms of these unknowns, solve them. The equilibrium equations are MBA plus MBC is 0, MCB plus MCD is equal to 0, solve them and draw your free body diagrams. After you get the end moments, you can get the reactions. You know there are two parts, look at this. After I get this end moment with plus and minus sign, this 120 is shared by these two equally as 60-60. This is called the direct shear due to the loading, and there is a moment shear. This divided by 4.5 will add up here to the right support and it will get subtracted here. So you can do that for all the spans. So you have got the complete free body, you can draw the shear force diagram, you can draw the bending moment diagram. I will conclude this with showing you what to do when you have a sway type problem. If you have a sway type problem, you have to find the chord rotations. If delta B is 5 mm and delta C is 10 mm, your AB rotates clockwise, your BC rotates clockwise, and your CD rotates anti-clockwise. You should first work out these known chord rotations. Then the rest is simple. You plug it back into those equations. You now have the chord rotations, but you do not have any fixed end moments. You can just check this out yourself, find the equilibrium equations and draw the free body diagrams. Okay, we will stop at this stage. You have an exam coming up. Wish you all the best. Thank you.